In this lesson, we are going to talk about the energy balance. Recall from the beginning of this chapter, we talked about the energy balance, which was an equation, and we had energy in and energy out. When we say energy balance, we mean the energy in should equal to energy out. So we have this picture over here. In this side of this scale, we have energy in, which is food or beverages, and we have energy out. This is the amount of energy we expend, like or energy expenditure. So overall, this is the concept of energy balance. And there are a couple of primary influences or factors that affect the energy expenditure, or over here we have energy out, which is the resting metabolism. We have physical activity, and remember from first chapter we defined the physical activity and different types of physical activity that can be any type of activity, exercise and sport. And also we have a smaller influence, which is the process of digesting food. So these three parts is composing our energy out part of the scale here. And when energy in balances with energy out over time, the person's body weight is stable. And whenever the energy in is higher than energy out, the person gains weight over time. And vice versa, like if the energy in is less than energy out, the person is losing weight. It's very simple, right? And here is another picture for this balance here, energy balance. So energy in is composed of drinks, food. These are the items that give energy. And the energy out, remember we said there are three primary influences on the energy out. We have the thermal effect of food, or this is the amount of energy we consume for digesting food. And most of the time we consider like 10%. This thermal effect of food accounts for 10% of total energy out, total energy expenditure. We have physical activity like exercise, any type of activity, sport. It's 20 to 30%. And the metabolic rate, it's 60 to 70%. So here we said resting metabolism. This resting metabolism is metabolic rate over here. So this is the components, three primary components of energy out. We can estimate energy intake, right? We can estimate our energy intake by using different methods and systems, one of which is self-reported food intake. We have like 1, 3, and 7 days food uh, diary or self-reported food intake. When we can use this food diary and self-reported food intake to estimate energy intake. And this self-reported food intake, they have like some common source of errors because they are self-reported, right? We can forget to record the snacks. We have to record all food and beverages, their types, their amounts. There can be some underreporting food intake or underestimating portion sizes. So these are the common errors regarding the self-reported food intake. But we can use this food diary for estimating energy intake. And as I said, we have the energy expenditure. We have total energy expenditure over here. This is total energy expenditure or energy out. It's composed of physical activity, thermic effect of food for digestion, and we have resting metabolism. If we add up these three components, we get total energy expenditure or TEE, sometimes TDEE, which stands for total daily energy expenditure. And this is the total amount of energy required by the body over the course of a day. So this total energy expenditure is reported as daily. And we have three discrete components or three primary influences. Resting metabolism accounts for approximately 70%. The thermic effect of food accounts for 10%, and physical activity accounts for 20 to 30%. And the resting metabolism is approximately 70%, but we can put a range here 60 to 70%. There are two different concepts here. We have uh, basal and resting metabolism. And there is a slight difference between these two. So when we say basal metabolism, it refers to the energy necessary to keep the body alive at complete rest. It can include like breathing, blood circulation, like the heart pumps the blood throughout the body, or the energy we need for nutrient absorption. We need energy to conduct nerve signals and overall the nervous system, and also maintaining body temperature. These are all require energy, and this is the basal metabolism or um, basal metabolic rate. And this basal metabolic rate is the measurement. So whenever we measure the basal metabolism, it's the basal metabolic rate. And it's a measure of the amount of energy per unit of time, which is per day, necessary to keep the body alive at complete rest. But on the other hand, we have resting metabolism. It's a state of wakefulness at different times. The room temperature is not precisely controlled, and it is about 10% greater than basal metabolism. And it's also referred to REE, resting energy expenditure or resting metabolism. And just like the basal metabolic rate, resting metabolic rate is the measurement of resting metabolism. I would like you to memorize these terms and know the differences. So when we say basal metabolic rate is the measurement of basal metabolism per day when the body is at the complete rest. And when we say resting metabolic rate is the measurement of resting metabolism. For the basal metabolism, there are a guideline for measuring the basal metabolism. The room temperature should be controlled precisely. The body should be at the complete rest, but the resting metabolism can be measured at different times, and it's the state of wakefulness. So let's answer this one together. Of the three components in total energy expenditure, the one that can be influenced most readily and to the largest extent by the individual is resting metabolic rate, physical activity, a thermic effect of food. Which one? Yes, that's correct, the physical activity. So we have 20 to 30% of total energy expenditure can be in the form of physical activity, and this can be changed according to different individuals based on their activity levels. For all individuals, the thermic effect of food is 10%, and the resting metabolic rate is 60 to 70%, right? But the physical activity can be changed a lot. And here, these are the factors affecting the resting metabolic rate. And here we have the factors over here, like sex, genetics, age, body size, like height. We have thyroid hormones, starvation, amount of fat-free tissue, exercise, environmental temperature. So whenever the temperature is high, it's too high or too low, like too cold, we consume more energy. Our body consumes more energy or expends more energy in order to maintain an optimal temperature. Or ascending to high altitude, caffeine intake and smoking. These are also increasing the energy expenditure. And ascending to high altitude also increases the amount of energy expenditure. So we have body size, height, and there is a positive relationship between body size with the resting metabolic rate. There is an inverse relationship between age and resting metabolic rate. Resting metabolic rate can differ between different individuals because of the genetic factors. Gender, we know like men, men are consuming more energy. They have higher resting metabolic rate compared to women. We have thyroid hormones. So based on the activity of a thyroid gland, we have hyperthyroidism and hypothyroidism. In hypothyroidism, the thyroid hormones is low because of the low activity of thyroid glands, and the resting metabolic rate among people with hypothyroidism is low. And among the people with hyperthyroidism, in who the level of thyroid hormones are high, resting metabolic rate is also high in those people. In this self-restricted food intake, we see a low resting metabolic rate. And also we have the columns, different columns, like these are the influence not under voluntary control. So we cannot control sex, we cannot control genetics, age, body size, or thyroid hormones. We have substantial influence on self-restricted food intake, an amount of fat-free tissue by doing some exercise. And these last four, we have subtle or temporary influence, and they are under voluntary control, meaning that we can change these factors, we can influence these factors in order to affect our resting metabolic rate. If we engage in more exercise, we can increase our resting metabolic rate. This is in our hand, right? We can control it. Or if we try to maintain the room temperature at a decent level, we can maintain our resting metabolic rate at a decent level as well. We can avoid like ascending to high altitude, or if we want to do some like mountain climbing, we can control this. Or caffeine intake and smoking, we have full control on these factors. And as I said, the metabolic rate of females is less than that of males by about 100. It's about 100 kilocalorie per day. And there are two factors to decrease resting metabolic rate in healthy people. Age is one. It's about 1 to 2% decline per decade. So in per decade, we have 1 to 2% decline in resting metabolic rate. That's why when we are aging, we are gaining more weight. We are gaining more body weight because we lose the resting metabolic rate substantially with aging. And also we have the starvation or famine or severe dieting. It's by 20% or more. So by doing some self-restriction or like in starvation or during the famine time, there is a 20% or more decrease in resting metabolic rate. And regarding the fat-free mass, when we say fat-free mass, this is the definition for fat-free mass. All the tissues in the body that are not fat, they are called fat-free mass, which we can say from the name by the name because it's like fat-free. It's without fat. So the tissues in the body that are not fat is called fat-free mass, and it has a like positive relationship or positive correlation with resting metabolic rate. Higher resting metabolic rates than fat mass. So fat-free mass has higher resting metabolic rate than fat mass or adipose tissue. This can be also one of the reasons why men are consuming more energy or they have higher resting metabolic rate compared to females because of like we know like male or men have higher fat-free mass. They are more muscular than women. So that's also can be a reason why we have higher resting metabolic rate among men. We can estimate the resting metabolic rate as we can estimate the energy intake by using like food diary. We can do also some estimation on resting metabolic rate. We have direct measurement, and this is what we see like in like the room calorie meter. That's the direct measurement for resting metabolic rate. Um, which in many cases it's impractical because of the costs and they require high technology. But besides the direct measurement, we have different formulas. These formulas are also called a prediction equation. These only estimates with a fairly large measurement error. We have Harris-Benedict formula or equation. We have Mifflin. This is less accurate with larger amounts of fat-free mass. So the Mifflin, we don't use Mifflin most of the time in athletes because they are less accurate with larger amount of fat-free mass or muscle mass. And we use Mifflin in clinical practice, like in hospitals or in clinical settings. Most of the time we use Mifflin. We have Cunningham, which is more accurate in athletes, and we have other formula or equations to estimate resting metabolic rate. But the for athletes and in sports nutrition, we use Cunningham and Harris Benedict. And this is the Cunningham equation. The resting metabolic rate equals 500 plus 22 multiplied by fat-free mass percentage. Remember, this fat-free mass is in percentage. So we have this one resting metabolic rate equation. For example, we have an example here. So estimating resting metabolic rate in a 23-year-old Caucasian non-obese female endurance athlete who is 5 feet 6 inches and weighs 135 pounds at 20% body fat. So she has 20% body fat. So we can conclude that she has 80% fat-free mass. And she has approximately 49 kilogram of fat-free mass. And by doing all these calculation, we get 49.1 kilogram. And if we put in the formula we get one 1580 kilocalorie per day. So in this example, they put the fat-free mass as kilogram, but I will show you there are other formula that has the fat-free mass in percentage. So in this case, if we like multiply 22 or 200 or 22, most of the time it's 22 by body weight in kilogram multiplied by fat-free mass percentage. So we can use this formula here, 500 plus 22 multiplied by fat-free mass in kilogram, or 500 plus 22 inside the parentheses, body weight in kilogram multiplied by fat-free mass percentage. For the Cunningham, we have to have body composition and fat-free mass. Otherwise, we cannot use this equation. There is also a simple estimate, which is the simplified resting metabolic rate formula. It is like this. For men, 1 kilocalorie per kilogram of body weight per hour. And for women, it's 0.9 kilocalorie per kilogram of body weight per hour. So, for example, we have estimating resting metabolic rate in a 23-year-old Caucasian non-obese female, like which is the previous example. So first, so we have the body weight in pounds, we have to convert it to kilogram by dividing by 2.2, and we get the kilogram for this female. And if we multiply this by 0.9, we get 55.22 kilocalorie per hour. And if we want to get the resting metabolic rate for 1 day, we have to multiply that by 24 and we get the 1320 kilocalorie per day. So if we compare this resting metabolic rate using the simplified equation or estimate with this one, with Cunningham, we can say there is a difference here, right? It's like 200, more than 200 kilocalorie difference between Cunningham equation and simplified equation. So I urge you to use Cunningham if we have the body composition, information and data of participants. Otherwise, we can use Harris Benedict, and I will show you the formula for that one too. So among the energy expenditure formulas and equations, Cunningham and Harris-Benedict equations are more accurate and common among athletes. We also have ballpark method, which is the body weight in pounds multiplied by 10 calories per pound. This is also another simplified method. It's ballpark method. We have Cunningham equation, it's 500 plus. There's a typo error here, I guess. This should be 22. And body weight in kilogram multiplied by fat-free mass percentage. So this is 22, not 200. And here we have another example. a 25 years old, 178 pounds, 5 feet 12 inches female bodybuilder with 23% body fat. Again, you have to be cautious. You have to be careful about this information here. This is 23% body fat. This is fat mass, not fat-free mass. So we have to do a 100 minus 23, which gives us 73 percentage of fat-free mass. And if we put in the equation, we get around approximately 1,872 kilocalories per day by using the Cunningham equation. And here we have the Harris-Benedict equation. The ballpark method is very simple, so you can memorize this. Cunningham equation is also very simple to memorize it and to remember it. For the Harris-Benedict, you don't have to memorize these formulas because for in the exams and in the quiz, if there is any question about this equation or formula, I will provide the formula for you. Harris-Benedict equation is most of the time is used by health professionals. And here is the formula. This is for men and this is for women. And also we can use the weights, body weights in pounds, heights in inches, and age in years. And here is the example. Again, the same example for the female bodybuilder. If we put in the formula, we get this is the basal metabolic rate. You can say it's like resting metabolic rate as well, because there's a slight difference between these two. We get this amount 1641.3 kilocalorie per day. And if we compare with this one, this is 1872 kilocalories per day. So there's a slight difference between these two. And we have the thermic effect of food. This is the second component of total energy expenditure. It's also sometimes it's called dietary induced thermogenesis, DIT, or thermic effect of food. This TEF is more common than DIT in textbooks and in research articles. It's the amount of energy required by the body to digest and absorb food and nutrients, and it depends on the frequency and energy content of the meals. And it's calculated by multiplying daily caloric intake by 10%. And in many cases, TF is not calculated or included in total energy expenditure uh, because of different reasons why we don't use thermic effect of food. Because the thermic effect of food is like we see an increase in thermic effect of food in energy expenditure for only 1 to 2 hours after eating. And these are the effects of the type of food on a thermic effect of food or TEF. Proteins has more effect than carbs and than fats on thermic effect of food. So if our meal consists of proteins only, we have higher amount of TEF. And this is the physical activity. As you can see from here, the sedentary person, A, we have physically active person, B, and exercise, C. You see, you can see from this figure, the thermic effect of food is the same among these three individuals. Resting metabolism is also the same, but the physical activity can be different. That's why we say physical activity is the only component that can be changed to a large extent compared to other two components of total energy expenditure. Physical activity, also referred to as activities of daily living or ADL. This is the personal care activities necessary for day-to-day living, like bathing, walking, grooming, dressing, so on and so forth. These are called ADL, activities of daily living, or physical activity as well. For physical activity component, we have a term called metabolic equivalence. Metabolic equivalence, or MET, MET, or MET, it is the level of energy expenditure equal to that measured at rest. And one MET is equal to the energy expenditure of an average resting metabolic rate. And the activity intensity, like the physical activity intensity or exercise intensity expressed in MET. So we have an example here. A task that requires 3 MET requires an energy expenditure level three times that of resting. So a 23-year-old female who wants to walk at a moderate pace for 30 minutes, her resting metabolic rate is 55 kilocalorie per hour. The MET for walking is 3.3. So the walking intensity is expressed in MET, which is 3.3. And as we said, 1 MET is equal to the energy expenditure of an average resting metabolic rate. So MET for walking is 3.3. And there is a table showing the MET for different types of physical activity and exercises. So she expends 55 kilocalorie per hour multiplied by 3.3 equals to 181 per 0.5 kilocalorie per hour multiplied by zero point 0.5 or 91 kilocalorie per hour. This is the total energy expenditure. Why we put zero point 0.5? Because it's 30 minutes, half an hour. So this should be zero point 0.5 to get the hour. And so we have the estimated energy requirement, or EER. This is another term. This is the estimated amount of energy that needs to be consumed to maintain the body's energy balance. And it is based on age, sex, physical activity, height, and weight. Here, this table shows the estimated energy requirement. So for the sedentary, we have light activities, we have moderate activity, heavy activity, and exceptional activity. And these are the estimated energy requirement. The first column is for female and the second column is for male. So when we say like 30, it's the 30 kilocalorie per kilogram of body weight per day. So for example, for me, let's say I'm a sedentary man, I require 31 multiplied by my body weight, let's put like 75. That amount of energy is my total energy expenditure per day. This is the estimated energy requirement. Let's answer this. Which of the following factors is most closely associated with the decline in resting metabolic rate in healthy individuals? So pay close attention to this decline. This is a decline. Yes, that's correct. That's aging. Because whenever we have an increased lean body mass, meaning more muscle mass, muscle are more like active organs than other tissues. So they require more resting metabolic rate. So we have an increase in resting metabolic rate in increased lean body mass. With higher protein intake, as we said, as we mentioned, proteins has more influence on a thermic effect of food, and the physical activity also has a positive effect on resting metabolic rate. So that's the correct answer is aging. Which statement best describes a metabolic equivalent? A, the amount of energy needed to maintain basal metabolic rate for 1 hour. A unit representing the energy cost of an activity as a multiple of resting metabolic rate. The number of calories burned per minute during vigorous exercise. The ratio of carbohydrate to fat oxidation during exercise. So the correct answer is which one? Yes, it's B, a unit representing the energy cost of an activity as a multiple of resting metabolic rate. And here, a female weighing 70 kilogram participates in a 6 MET activity for 45 minutes. What's her total energy expenditure? You can pause the video and try on your own and then watch the video. So let's do this together. The correct answer is B. So we have to multiply the body weight 70 by 0.9, which is 63 kilocalorie per hour. And we have to multiply this by 6 because we have 6 met. We get 378 kilocalorie per hour. Why we put 9 here? 0.9 because female, this is a female, and this is the simplified equation, right? We said for men it's 1, for female is 0.9. So body weight multiplied by 0.9 because the participant is a female, and we get 63 kilocalorie per hour. We have to multiply that by MET, which is 6. We get 378 kilocalorie per hour, and we have to multiply that by 45 divided by 60 to get our, because we have 45 minutes, and it gives us 283.5 kilocalorie for 45 minutes of activity.